we roll, man. Some rock, some win, some 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 win, man.
Hi, my name is Loris Crow, and we are executing a showtime. Zig SHOWTIME is a show and a community for makers. Oh no, what's going on with my video? Okay, that was interesting. Thank you, OBS. What do you know? Surprises. So Zig SHOWTIME is a show and a community for makers. Watch the show to learn about interesting projects and join the Discord server to share what you're working on and to collaborate with other members of the community. And if that's not your style or you're new to Zig, make sure to check the other Zig communities to find the one that suits you best. So it's been a long break, and as you can see, OBS updated. There's been a lot of news, so it's not just OBS that updated, but we also have a few things. So let me go through them before we start. Well, you know what today's episode is all about, right? Viewstamped Replication. I think we made a good job at explaining all the interesting stuff that's going on. But before that, let's go through some Zig news. So first of all, 0.8.1 has released. Also look at the cute zero art. And by the way, it's just bug fixes, right? 0.8.1, that's minor release. Sorry, that's a patch release. Then next, alongside the new version, we also published a blog post, Maintain It with Zig. I really recommend you check it out, especially if you have like a C++ code base that you have to maintain. And there are ways in which Zig can help you, even if actually you're not interested yet in moving to Zig. Next thing, Zig Monthly. So Zig Monthly is a new newsletter. You know how monthly newsletters usually work for programming languages, I would assume, because all of them have at least one. And now we too have our monthly newsletter that keeps you up to date with, you know, the latest and greatest that's happening in the Zig world. Then after that, Zig News. So this is a website that I set up a while ago. It's zig.news, that's the full URL. And it's a blogging platform, which is entirely dedicated to Zig. It uses the same content management system that dev.to uses. And I think it's great for people that maybe kind of want to write something about Zig, but they also don't want to maintain their own blog. Some people do, some people don't. And I think it's a good way of, you know, without too much effort, you know, also even just to, what's the expression, to taste the waters. So if you're not sure that blogging is for you, you can try with Zig News, and then you can move your content away on your own blog once you decide that you want to get more serious about it. What's also neat about this is that there's this problem where if you have a blog website, but you don't blog much, what ends up happening is that you write something, and then whatever you write is like thrown into the void. Like you have to publicize it, otherwise people won't even know that it exists. And Zig News also solves this because it has an integrated, you know, homepage with a recommender system and stuff. And it also allows you to like keep track of, have an idea of if people are watching, are reading your stuff or not. So I think that's kind of neat to get started. Next, this YouTube channel has surpassed 2,000 users. Thank you very much to everybody that has subscribed. It's only 98,000 subscribers before I can finally get my YouTube degree, but hey, I'm sure it's not gonna take long. Next thing, Andrew in a podcast, full-time open source. You might want to check it out. How do you work full-time in open source? That's not easy. Not a lot of people can do it. And this is a discussion on how Andrew was able to do it and related stuff. So great podcast interview. Next thing, NDC Oslo, if you happen to go to NDC Oslo, or you know somebody who is going to NDC Oslo at the end of November, if they want to learn more about Zig, tell them to come to room whatever at the right time, and hopefully I'll be there. Finally, Handmade Seattle. So Handmade Seattle is also happening in November, and you can see that November 11th, Andrew is going to speak there. I would really love to be there too, but as things are right now, it doesn't really seem that it's going to be possible. I hope things will change before the date, but for now, we don't really have... it's going to be easy for European people to be there. Well, rather, it's not possible right now. Hopefully this will change. And I think these are all my news. So today's episode is going to feature a talk by Joran about Viewstamped Replication. Then we're going to have an interview, a pre-recorded interview with Dr. Oki. Then we're going to have a chat, like a live interview with James Cowling, and both of these people are the authors of the Viewstamped Replicated papers, and alongside Barbara Liskov. And at the end, we're going to have an announcement by the TigerTeam. So lots of stuff. I would say let's get started. So we're going to start with Viewstamped Replication made famous by Joran. And this might be hard to believe, but this is going to be a cinematic slide deck. So sit tight and enjoy the ride.
Greetings, Laurice.
Hello.
How are you feeling today?
I'm fine. How are you?
Excellent. Great to be on Showtime. Shall we play a game?
Love to. How about Total Order: Rise of the Replicated State Machines?
Wouldn't you prefer a good game of Viewstamped Replication made famous?
What's that?
It's a game where you design a distributed system for optimal high availability and see if someone can hack it.
Okay, tell me how to play. The stream is yours, and your time starts now.
Wait a minute, Laurice. Are you telling me that Showtime now has a time limit?
Yeah, and the timer started already.
Oh, well, meet the client. Clients are friendly, very friendly. They can be wealthy with bags full of financial operations they want to keep safe. But while they're friendly and while they have bags full of financial operations they want to keep safe, they're also pressed for time. And they don't like to be kept waiting. In other words, they're loaded down with all kinds of valuable things they want to store safely, but they have little time. And that's because the other trouble with clients is that clients come and clients go. And if you're not available for them when they need you, then they might not show up again. But wait, whose clients are these? Why, these are the clients of TigerBank, a financial institution whose pillars are the foundation of trust, where the grass is always trim and the trees grow tall. You could even say the sun shines at TigerBank, and the vaults are never half empty, but always half full. But TigerBank, for all its charms, is still a traditional institution, a brick and mortar kind of bank, the kind where you sign your checks on paper And the clients? Well, the clients are starting to think different. The clients want to bank on their phone. They don't like waiting. They want to be on the line, not in the line. And that bag full of paper IOUs is now a phone full of payments too. What did TigerBank decide to do? To keep the grass trim, the trees tall, the sun shining, and the vaults half full? Well, they decided to spin up something called a server, to be like the teller at the bank, but instead of serving walk-ins, it's going to be serving requests from clients' phones. Clients are going to dial long distance into the server through their phones. Say howdy and hi, and then put some of their precious IOUs into a little red bag and send it over the wire. A little red bag called a packet. And TigerBank have got a special name for this packet. They're going to call it a request. But the amazing thing they dreamed up with this design is that the clients just put these financial operations into a little red bag called a request and send it off like it's FedEx. The impatient clients don't even need to hang around for their requests to get to the server. They just ship it off and say prego and ciao, and everyone is happy. And this is also going to work great because the clients really like TigerBank, and because the clients also know that they're coming and going so much that it's very easy for a client to lose a phone like this, or like this, or like this. Whereas TigerBank still has these vaults that are half full to store this new server machine safely. And these vaults are obviously completely waterproof, tractor-proof, and pirate-proof. But the best thing of all is that these half-empty vaults, half-full vaults, even have bonus space for the backup machine. So the Tiger technicians, as a bonus, are going to 2x TigerBank's durability. The backup machine is going to copy from the primary server machine exactly on the hour, every hour, using something called a Tron job, because everything happens like clockwork at TigerBank. And this copying trick to back up the primary server is also going to use some revolutionary consensus technology called the File Transport Protocol, or FTP. In fact, one of the IT staff became so convinced that this would be most efficient after reading a Hacker News comment. That was the top comment, that it's trivial to use FTP to synchronize your backup with your primary machine. So they're going to connect the primary server to the phone line and let clients dial in and shoot off these one-way requests in little red bags called request packets. And then they're going to have two people sitting in the vault so that if the primary machine crashes, they can just unplug the phone line from the primary machine and plug it into the backup machine. Now, this system was all set to launch when a very fastidious employee at the bank called Mr. McKittrick made the right call and stopped the launch. Because he was a very risk-averse employee. After all, TigerBank was a happy place, where the grass was trimmed, the trees tall, the sun shining, and the vaults never half empty, but always half full. If there was a word to describe TigerBank, then it would be hard to find a better word than staunch. So Mr. McKittrick said, maybe we should test all this new dial-in service stuff with bonus backup and FTP before we launch. And he began to dial the number of an old friend from school called Bishop. Now, Bishop was a cool character. He was called Bishop because he was a chess player and because he had an interesting line of work. Banks would call Bishop up and hire him to think 3 moves ahead, to find ways to break their new dial-in servers, to make sure that no one else can break their new dial-in servers. And Bishop was cool, not only because he thought different or because he looked like he listened to jazz, but because one of his bank jobs had even been made into a movie, about running shoes. Of course, it didn't take someone like Bishop long to think through what was wrong with the bank's new dial-in service system. In his report, Bishop wrote, and then underlined in red, that the new system was not highly available and would keep clients waiting while the technicians reacted to a crash of one of the machines by swapping phone lines to the backup. Bishop understood that the primary server might crash at an awkward time, that it might take too long for the two technicians both to agree that it was in fact crashed, and that the technicians might easily forget which was the primary. Which was just another clue that the system was definitely not fault tolerant and could not be trusted, because the clients were sending requests in fire and forget fashion. To illustrate this point, Bishop evoked the image of the cable monster, a disgruntled telecoms engineer in the neighborhood who would at times play tricks on people who were busy dialing into their servers by rerouting or replaying their phone calls. But in the case of TigerBank, if the cable monster in the network were to cut the wire after a client sent a financial operation, deleting it from its own phone, but before the server were to receive it, then all the money in the operation would be lost. And just as bad, if the cable monster were to record and replay these calls, then money would be paid many times over. Sadly, the system was also not durable and would not keep the client's operations safe. In his inspection of the vault, Bishop found a rare breed of beetle that would have been very attracted to the aluminum in the batch of identical hard disk drives that the technicians had purchased for a discount from the same vendor. And so it became evident to Bishop that if the beetles did not get to eating the aluminium in both disks, then a manufacturing quality control issue from the vendor eventually would. But if the beetles did get to a financial operation on one machine, then Bishop would have expected that this machine would repair itself using the copy of the financial operation from the other machine, even if both machines were being corrupted in different places. Sadly, however, there was no such provision for any automated recovery from corruption or data loss. And of course, because backups were going to be taken precisely on the hour, there would always be many minutes of financial operations lost in between backups if the primary were to fail permanently. Unfortunately, the system was also not consistent. And even if the primary were to fail temporarily, when it came back up, its data would be inconsistent and irreconcilable with the backup that had been running in the interim. It was also possible that the technicians might forget to swap the FTP job around when they swapped the phone lines. Thinking 3 moves ahead, Bishop could see a time when the two technicians might be in the vault, half awake, with the FTP backup mechanism set to back up to the wrong machine. The clock would strike the hour, the FTP job would run and overwrite the server's more up-to-date data with the older, less up-to-date version from the backup, destroying data on the server and causing the primary server to crash as its files were deleted, which would set off an alarm and wake technician number 1, who would ask, "What?" Then swap the phone lines to promote the backup to be the primary and swap the FTP job around before going back to sleep. Before the clock would strike the next hour, the FTP job would run again and replace the data on the primary server with yet more stale data and crash the primary and wake technician number 1 again, who would then wake technician number 2 with his shout of, "Oh no." The launch would not have been a success. This new system was not a marvel. It would still keep clients waiting to store their financial operations before going out of its way to lose them or mess them up. Bishop emphasized again that FTP is not a consensus protocol. And finally, because this misinformation seemed to be at the root of the problem, in his report, Bishop concluded, by referring TigerBank to a brilliant young student who had pioneered the field by writing "Call Dr. O." Everyone at TigerBank was so amazed and impressed with Bishop's report that they paid him a $3,000 bounty in addition to his contractual fee, immediately promoted Mr. McKittrick, and then went looking for Dr. O. He was called Dr. O because he would design original algorithms that would make the suboptimal optimal and the impossible possible, so much so that people would sit up and say, "Oh," especially the professors in his field from leading universities such as MIT, Cambridge, New Hampshire, and many others. Because not only was Dr. O's work original or optimal, it was also so clear and elegant, making the formal ideas informal in a way that was readable and ahead of its time. And when Mr. McKittrick and everyone had flown Dr. O over to the TigerBank office, and when they had all sipped some of their homegrown, homebrew Tiger Tamarillo, and when they had told Dr. O that their clients wanted high availability, fault tolerance, durability, and consistency, this is, more or less, exactly what he said. Right, everybody, first, we're going to need more bags. To solve the problem of the cable monster that occasionally eats packets when clients dial into the server, we need a little red request packet bag for clients to send financial operations, yes, but then we also need a little orange reply packet bag for the server to reply and tell the client the result of the request. This way, the client doesn't delete the financial operation until it knows it's safely stored on the server. And if the client goes away quickly before it gets the little orange reply packet, then it can just say hello again and resend the request until it gets the reply. When it gets the reply, then it knows it is safe to delete the financial operation because it's stored on the server in the vaults. And we'll include a little number in each client request packet so that the server can ignore duplicate requests. Speaking of the server, we need to rethink the way we think about what's inside the server. The trouble is, up until now, TigerBank, you've been using the plural servers, a primary and a backup, i.e., multiple personalities, instead of the singular server, i.e., a single personality, and this is leading you into trouble. What we need to do is take the concept of a server and keep it singular. We only want TigerBank to ever have one server, so clients only ever see one server. I know what you're thinking, only have one server? But let's take a look at what's inside this new breed of server. We've taken all the expensive big iron and turned it into 3 smaller machines that all work together to appear as a single logical server. We've gone from multiple physical servers to one logical server so that we can have one consistent set of data and be a single system of record. But that's also going to be much more fault tolerant and durable, as we shall now see. To solve the durability problem, let's pretend that the phone line is just always connected to the first replica, replica 0. Then, when the client sends a little red packet to the server, this will arrive through the phone line that's connected to replica 0, which is the primary machine, because that's the machine that's answering the phone line. Now we're going to do a cool magic trick. So when replica 0 receives the little red request packet from a client, before the primary ever sends the reply back to the client, we're first going to have the primary put the little red packet inside another bag, a little blue packet called a prepare packet, and then send it to the backup machines. First, to the next replica after it, which is replica 1. And then in parallel to sending the little blue prepare packet to replica 1, it also sends the same prepare packet to itself, so we can always just reuse the same code path for handling these prepare packets when we receive them. Then as soon as replica 1 receives the packet from replica 0, which because they're in the same vault, it's a split millisecond later, Replica 1 in turn forwards the prepare packet onto replica 2, completing the replication circle. While this is happening, replica 0 has finished storing the packet and sends an OK packet back to itself. Again, just so we can always have a single code path to handle the OK packets we receive. Then replica 2 also sends the OK packet to replica 0. And now replica 0 can reply back to the client, knowing that the client's request is safely stored on 2 replicas, so that even if a whole replica machine is dropped in water or destroyed by a tractor or stolen by a pirate, the client's request will not be lost, but will be durable. Notice also how small these little OK packets are. They're so small, they're very lightweight. And also see how, while we pass the prepare packet, each replica also sends the OK packet directly back to replica 0. But why do we want to reply before replica 0 receives the OK packet back from replica 1? Let's take a look at how we count these OK packets with something called a quorum counter. When the client's request arrives, we start to replicate it to ourselves, and then to replica 1, and then replica 2. So we haven't received any OK packets yet. While this is the case, we might decide to resend the prepare packet, and perhaps we might leapfrog replica 1, just in case it's crashed and can't forward for us. But then at some point, we receive both OK packets. And then we can see that, okay, replica 1 is either slow, maybe because the hardware is slowly failing, something called gray failure, or it might be temporarily slow, maybe the solid-state drive is doing a garbage collection. Or it might even be that replica 1 has just crashed. So it makes sense that we reply after 2 OK packets, because this way we can make TigerBank super fast without slowing down for the slowest replica. But why do we do this past the prepare packet game? Why don't we just have the primary machine itself send the little blue prepare packet to all the other replicas? Like so. Because, as Dr. O told TigerBank, it's not optimal. And here's why it's not optimal. Imagine that replica 0 can receive 100 packets per second and send 100 packets per second. If replica 0 now has to forward a little blue prepare packet to the other replicas, and if the server contains something like 5 replicas in total, then this means that replica 0 has to forward the big prepare packet 4 times, which divides the number of packets that replica 0 can send from 100 packets per second by 4 and becomes a bottleneck. And this is also not optimal and even makes the logical server unstable, because this also places more load on replica 0 compared to the other replicas. Let's count how the messages are sent. All the replicas receive 1 big prepare packet, but then replica 0 is the only replica that sends 4 big prepare packets. The little blue OK packets are so small that they don't make much difference. So we can see that the load on replica 0 is really driven by the big prepare packets it has to forward to all the replicas. And this load is unevenly distributed. And that's not optimal. Let's see now how our pass the prepare packet game does if we count our messages. Again, all the replicas have to receive the big prepare packet, so that's 1 for each of them. But then the magic happens, and each of them play their fair share of sending the big prepare packets to other replicas. And we can already see this is optimal, because the load is now evenly distributed, no matter whether a machine is a primary or a backup. And so, said Dr. O to everyone at TigerBank, this is how we solve durability optimally. But what about order? Clearly, the client's financial operations might depend on other financial operations, and we don't want to allow overspending. Here's what we need to do to make sure that all the replicas get the financial operations in the right order. First, we must understand that clients might say hello at the same time. Here's client A with request 1, client B with request 42, client C with request 100, and each of these are the number of requests per client. So this is client C's 100th request. They are a centenarian. And then client A's request number 1 gets replayed by the cable monster. The problem we want to solve is how to get these requests into the log in exactly the same order on every replica, so that we're putting these little blue prepare packets into the log like this, and like this. That almost looks like my uncle's old recipe, curry in a hurry. Back to order. Because we have replica 0 as the primary for now, this is pretty easy. We just have replica 0 keep a number in memory called the prepare operation number, or op number for short. Then as each client request arrives, we assign it a number. Let's say that replica 0 has already processed 699 ops. So our op number is at 699. Then C arrives first, so we append op number 700 for client C to the end of the log. Then A arrives, so we append A's op to the log as op 701. Then B arrives, so we append B's op as op 702. And then A's first request arrives again, but we just ignore it because we can see that A's first request is already in the log. Now I know what you're thinking, predicts the prescient Dr. O. How do we go from this log to executing these financial operations and acting on the client's financial instructions? Simple, we use a functionator. Yes, a functionator. A functionator is nothing more scary than a simple function that will take all your account balances and the current financial operation you want to execute and then return the result, which the server can then send back to the client in the reply. And really, the beauty of the functionator is that it is what it is, a simple bring your own function that you could change to any function you like. And so we return again to our question. Now that we have a beautifully pure functionator, which is simply a function, how do we go from the log to executing operations through our function? Simple. We have the replica track another number called the commit number. Then if our commit number is 699 and we see that we have replicated op 700 to enough machines, we simply run op 700 through our functionator and bump our commit number from 699 to 700, and so on, and so on. And there you go, said Dr. O. Fault tolerance, durability, order, even a functionator. But how do we swap the phone lines and the primary replica automatically? Well, Dr. O said that there were at least 2 ways to swap the phone lines, depending on a number of factors. And so Dr. O introduced them to somebody just as special, who was the professor, who taught Dr. O how to think about all these things and how to optimize and make trade-offs. Now the professor was elegant in every way, and in fact so elegant, and had contributed so many elegant ideas to the field, that a Turing Award had been given to the professor to say, thank you for the amazing things that taught people how to think and see the world of computers in new ways and speak new languages to computers, languages even written by the professor, and all so that people could learn to express new ideas that the professor had also discovered. In fact, the professor created programming languages that were so incredible that her programming languages, just like Bishop, would go on to become movie stars in their own right, where, just like her Viewstamped Replication, they would strive to create the perfect order and become famous for saying things like, "Greetings, programs." But despite all the fame, they never forgot about the professor and always took the effort from time to time to send a short pager back from the grid just to say, "Thank you, Professor." Now, in addition to Dr. O, the professor had also served as Jedi Master to a young Skywalker called the DJ. He was called the DJ because he was a disc jockey who would play at all the weddings for distributed systems gurus getting married, where he would play 70s, 80s, even 90s distro music, which was the kind of music he loved to play. He was also called the DJ because his name was James and because he was a doctor who could create the most awesome remixes of any kind of distributed protocol. And he could create these remixes not only because of the professor's help, but also because he was a wizard with a special magic pocket. Now, to decide how to swap primaries automatically, to decide which replica should answer the phone line, the professor and the DJ had in fact remixed one of Dr. O's protocols. And this remix was so amazing, it was basically VR, that is, virtual reality. Not only because it gave each replica a way to see how the primary replica, who the primary replica should be, as Dr. O's protocol had also done, but because it was so magical, you could even predict who the next replica should be. And all by adding something as simple as an in-memory number called the view number. The way the magic worked was that if a replica's view number was 0, and then if you took the mod of the view number 0 by the number of replicas, then you could immediately see that the primary would be replica 0. And if that was replica 0's view number, then replica 0 would answer the phone, otherwise it would just let it ring. You can see now that all of a sudden we can have 3 phone lines coming into the logical server. Clients can call any phone number they like, and then each replica can just decide whether to answer their phone depending on their view number, who they see as the primary. So if the view number is 1, then replica 1 would see itself as the primary and answer the phone line. And if the view number was 2, then replica 2 would answer the phone. To add to the magic, this would also have the effect of freezing to ice any previous views. So as soon as a replica learned of a newer view number, it would stop answering the phone for that view, and the old view would gradually freeze over. Then as the view number went higher and higher, it would just rotate the primary across the replicas and back to replica 0, who would then answer the phone again. The 2 technicians were so excited by this virtual reality, they wanted to know more. And this is, more or less, exactly what the DJ said. We always start with replica 0 as the primary because we always start with a view number set to 0. If the other replicas stop hearing from the primary, they stop getting prepare packets from the primary, then eventually they decide to bump their view number. If replica 1 notices first and goes, then it bumps its view number from 0 to 1, and it also freezes its view number so that it doesn't answer the phone just yet until it knows that enough of the other replicas also know what the new view number should be. Then it tells the others to start the view change and bump their view numbers to 1, and when replica 2 gets the start view change packet from replica 1, it bumps its view number to 2 and also freezes and sends the start view change packet to all the other replicas. Now replica 2 can already see that it has bumped its view number to 1, and it also knows that replica 1 has done the same, because, as you will remember, it received the start view change packet from replica 1. So it knows that 2 replicas have sent start view change packets. And then replica 1 receives the start view change packet from replica 2, so it also knows that 2 replicas have bumped and frozen their view numbers and set them to 1. So now they do something special. Replica 2 sends its latest op to replica 1 in a single packet, and this op includes the cryptographic checksum of the previous op, and so on, like a daisy chain or a hash chain. It only needs to send the latest op, which is op 800 for replica 2, so it sends it in a single packet to replica 1, like this. And then replica 1 can see that it only has ops up to 502, whereas replica 2 has op 800, so it sets its latest op to op 800, and then it asks replica 2 for the other ops to catch up. And then when replica 1 is all good to go, it unfreezes its new view number, and then it tells the other replicas to unfreeze their new view for view 1 and start the view, and it does this by sending a start view packet. And if this whole repair process takes too long, if replica 1 is more than a few milliseconds behind or a few hundred, then the other replicas will just do the same view change and bump their views and so on, and we'll get to the replica that's got the latest log. So this repair really doesn't delay the view change at all. And this start view packet, which the other replicas receive, then contains just the latest op 800, again in a single packet. And this is enough with the daisy chaining for the other replicas to catch up and then unfreeze their views. Having completed the view change, and all of this automatically within a few split seconds, replica 1 begins to answer the phone as the new primary. And so with the normal protocol and with the view change protocol in hand, the technicians quickly got the new system going, and McKittrick brought Bishop back again, and Bishop helped to bring these protocols to production with some simple designs like the packet bus, which was really just a way to keep all the packets and phone lines neat and tidy and provide a simple way to send packets from a client or replica to another replica just by knowing the number of the replica, or to send a packet from a replica to a client just by knowing the unique 128-bit ID of the client, without any IPv4 phone lines getting tangled throughout the protocol code. And also enabling multipath routing, where the client can send a message to one primary, then a view change happens, and then the client gets the reply straight back from the new primary. How cool is that? Much better than RPC. But what the technicians really liked was the design they came up with for the replica. The replica was just the code that would be run on each replica machine to execute what had now become known as the Viewstamped Replication, or VSR protocol. The cool thing with the replica was that it only had two public methods: a way to tick the replica, just like you would tick the second hand of a clock, so you could tick the replica as fast or as slow as you liked, and a way to pass a packet to the replica. With a simple design, the replica was now like an automaton that you could play, rewind, or fast forward exactly the same way every time. These designs for the packet bus and replica in turn allowed for the creation of the VOPR, which simply stands for Viewstamped Operation Replicator. The VOPR was a whopper of a deterministic state checking simulator that the two technicians could run beyond the clock to speed up time and simulate all kinds of ways that clients might greet the server, or that beetles might eat the aluminum material inside the hard disks. So that even if these beetles evolved into little techno beetles called TigerBeetles, the VOPR would be able to check that everything worked, and most important of all, that everybody was happy. And so it happened that Tiger Bank remained an institution whose pillars were the foundation of trust, with the grass trim, the trees tall, the sun shining, and the vaults never half empty, but always half full, with the exception that now the phone lines were humming, the clients were calling in transactions like crazy, and the two technicians, well, they thought this was all kind of magical. Grazie, Loris.
Wow, Joran. You really gave an amazing talk. Thank you very much. I'm sure people have enjoyed it a lot. Also, I'm reading the comments. People are enjoying the references a lot. That was an amazing talk. So let's see if people have questions. Let's not spend too much time in the Q&A because we have a lot of things to do. But if anybody has any question, you have very quickly a few seconds to type them up, and I'll reroute them to Joran. In the meantime, let's see, what question could I ask you? Are meetings at when you're like developing TigerBeetle, are meetings like this? Like usually people prepare slides, boring slides. At best they have transitions, like full animations. Like, do you do this stuff also at work every day?
You mean Tiger Bank, Loris?
Yeah, Tiger Bank.
Yeah, no, absolutely. We do these meetings just like this. And in fact, this is what we'll be using for our next meeting, as we all discuss Dr. O's principles and the DJ's ideas and the professor's ideas. But no, this is a one-off. we don't do it like this. I would love to. It was so much fun just drawing these sketches. I'm a terrible drawer with pen and paper, but I used the iPad for the first time, and I felt like Picasso. So hopefully we'll use these in in future meetings.
The visual style was very good. I enjoyed it a lot, so I think people have enjoyed it too. So it seems that people are pretty satisfied with the explanation. You were very thorough. You went from the basics. Yeah, banks sending. Can you imagine banks sending financial transaction information via FTP? That would be crazy. Like, imagine if the world was really like that.
I think today they don't use FTP anymore. It's just SFTP, so it's the secure version. You know?
Yeah.
But I've seen quite a few of them still do that, the way they send their data.
Yeah,
But,
yeah. Oh man. Okay, so next on the table is the interview that we pre-recorded with Dr. Oki, and would you mind give an introduction to Dr. Oki? In the meantime, I'll put on screen a couple of images that he shared with us, a couple of pictures from, at the time, the original paper is from the 80s, right? Well, do you remember the precise date?
88.
88. So it's from 88. And by the way, we can still see your screen.
There
Oh,
we
you
are.
have them there. Okay, awesome.
Yeah. So shall I just give a little intro about what these photos are about?
Yes, please.
Okay, thanks, Luis. So is it a game or is it real? Well, it's not just a game. This actually took place in history. In fact, this is the very building where the pioneering Viewstamped Replication protocol was born. This is basically the protocol that kick-started the field of consensus. It was the original optimal protocol, made the impossible possible. And I don't think this building is there anymore. And this is, in fact, a photo that Dr. Oki took as a young student in the 80s. This is also what he took. You can see there's a very special professor there at room or office 528. There's Professor Liskov, a pioneer in her field. And this is Dr. Oki's dissertation that he published in 1988, Viewstamped Replication for Highly Available Distributed Systems. And this is the paper that was born of that, which was presented, I think, in the same year. So Dr. Oki has asked us just to let you know that he is on sabbatical, and we hope you enjoy this special interview that we were able to record with Dr. Oki just before he went on sabbatical. Over to you, Luis.
Thank you very much. So I guess let's play it. I'm here today with Joran, who will help me interview Dr. Brian Oki to learn more about the history of Viewstamped Replication. How are you, Joran?
I'm well, thank you, Luis. It's great to be here on Zig Showtime with you. I'm really excited to dive into a special moment in the history of computing and to have this opportunity to speak with one of the great pioneers of distributed systems, Dr. Brian Oki.
Dr. Oki is the first author of the original Viewstamped Replication paper, which, in the view of many, pioneered the field of consensus. Dr. Oki, how are you today?
Joran and Luis, thank you very much for having me. It's a pleasure to be here. It's really gratifying to see continuing interest in Viewstamped Replication.
Can you tell us about the history and development of the original Viewstamped Replication? What did the world of distributed systems look like in 1988 before your doctoral dissertation was published?
Luis, distributed systems research was in its infancy in the 1980s. I joined Barbara Liskov's programming methodology research group at MIT in the fall of 1980. It was 2 years after Lamport's seminal paper on time clocks and the ordering of events in a distributed system, and it was 2 years before Bruce Nelson's doctoral dissertation on remote procedure call at CMU. Remote procedure call and message passing were the foundation of communication in distributed systems. MIT researchers competed with other universities and research labs. So what was the landscape of replication algorithms like in 1985? There were roughly two classes of replication algorithms. First, there was quorum consensus, exemplified by weighted voting in virtual partitions. Second, there was primary copy, exemplified by two commercial offerings, Tandem Nonstop, and Origin, and a paper on resilient sharing of distributed resources. And remember, the terminology back then in the 1980s was not master-slave or leader-follower, but primary backup. The best-known replication technique was Gifford's weighted voting, also known as quorum consensus, a generalization of majority consensus. Read and write quorums needed to intersect in order to guarantee that reads always read the latest written data. In the real world, Tandem's nonstop system and the Origin system were both based on the primary copy method, which is one backup, so it could only survive a single failure. The process pair was the centerpiece of both systems.
How long did the process take? What were the easy parts or the difficult parts, and how did the breakthrough insights happen?
Larice, the process took about 3 academic years from start to finish. Of course, with doctoral dissertations, you never really know in advance if the research is going to hit a dead end or take a detour. I started the research considering guardian pairs, like the primary backup process pairs. After some months, it was really clear to me that in order to tolerate no crashes and partition failures and continue to provide service in an asynchronous network, I needed to extend the number of backup guardians to 2 or more backup guardians, not merely pairs. So the easy part was reading previous work in the area of high availability and replication. The hard part was figuring out a novel solution that solved the guardian availability problem and yet distinguished itself from related work. There was no primary copy technique we knew of at that time with multiple backups that worked in a general asynchronous network with node failures and network partitions. So, did I have epiphanies and a single flash of inspiration? No. My insights came out not in any kind of single eureka moment, but steadily over the next 2 years.
Dr. Oki, in particular, how did you arrive at the elegant view stamp at the heart of Viewstamped Replication? The view change that would elect a new primary, and how did you ensure that events known to a majority of machines would survive across crashes? These 3 concepts, the view stamp, the view change leader election algorithm, and the intersection property, seem to be the 3 major breakthroughs and contributions of the work that would completely pioneer the field of consensus.
Joran, to understand this, let's start at the beginning with some context and terminology. Even though I realize that I'll be compressing much technical detail into a few minutes, and I might lose some of our listeners, I feel it's necessary to set the stage. I hope our listeners will find the explanation accessible and understandable. In the 1980s, Liskopf's research group was designing a new programming language and system called Argus to support the implementation and execution of distributed programs. It was an incredibly fruitful area of research, combining knowledge of programming language design with operating systems, networking, and relational databases. The main data abstraction of the programming language was the Guardian. Guardians encapsulated a set of resources and permitted those resources to be accessed only by means of methods that can only be called by other Guardians. Argus allowed computations to run as atomic transactions. It was in the context of Guardians that I started my doctoral dissertation research in the fall of 1985. While Guardians and atomic transactions solved the problem of concurrency and failures, it did not solve the problem of availability of the Guardians and the services they provided. When the Guardian crashed, the computations, which were run as atomic transactions, aborted and rolled back. But the service was unavailable until the Guardian restarted. The question that faced me was, how do we make Guardians highly available? By highly available, we meant the probability of providing service to clients in the face of failure was very high. We called the set of Guardians implementing a service a module group. This group behaved as a single logical entity. The group was organized into one primary replica and multiple backup replicas. During normal operation, read and write operations were executed only at the primary as part of a transaction. These operations generated events that were assigned timestamps. The primary propagated these events to the backups and were processed at each backup in timestamp order. The backups will end up in the same state if they execute the same sequence of events in the same order. For a transaction to commit, the backups needed to know the same events as the primary. All this sounds straightforward. right? Well, no. Only in an ideal world where nothing bad ever happens. Node failures and communication failures complicated this picture, especially when the primary failed or was partitioned. This was where my thinking started. In what ways did failures affect correct operation? And how do we preserve correctness in the face of such failures? Suppose the primary crash. Suppose a new primary was elected from the set of backups. How can you be sure that the new primary knew the same events as the old primary? How can you tell what events the backups did know? How did the backups know they have all the necessary events? What was the criteria to elect a new primary anyway? Some techniques back then depended on distinguishing node failure from partition failure. They might work with node failures, but not with partition failures and vice versa. View stamps were invented to solve the problems posed by these questions simply and elegantly. They depended on views, view IDs, and timestamps. So we defined a view as a set of replicas capable of communicating with each other together with which replica was the primary. The view was dynamic, adapting to and reflecting changing communication patterns among replicas. A view must contain at least a majority of the guardian replicas of the module group configuration. The majority requirement is key. We'll see why in a moment. Replicas in a module group configuration exchange periodic "I'm alive" messages. If a replica noticed it wasn't talking to another replica in its view, or it noticed it's communicating with a replica it could not communicate with previously, it initiated a view change. The purpose of the view change algorithm was to ensure that events known to a majority of replicas survived into subsequent views. It ensured that every view contained at least a majority of replicas and started up the new view in the latest possible state. So if every view has at least a majority of replicas, then it contained at least one replica that knew about any event that was propagated to a majority of replicas. The state of the new view included what that replica knew. This is why we needed a majority in any view to ensure that views intersected and included at least one replica that knew the events propagated to a majority. If the majority of replicas agreed to the new view through consensus, the replica switched to the new active view. Each view was identified by a unique view ID. The view IDs were guaranteed to be totally ordered. The view was not enough, however, because we needed information about the committed and active transactions that had run in the view. Originally, I thought that to determine if a backup replica knew it had enough information to take over from the primary, we'd have to send the entire transaction tree in messages to the backup replicas. Clearly, this sort of checkpointing was way too expensive, especially if it were done during normal operation. Was there a better way? Yes, there was. We borrowed an idea that timestamps could be used to track information flowing around the system. The timestamp captured this needed information. Timestamps were unique within a view and they formed a total order. Timestamps were an inexpensive way of determining what information survived a view change. Since a timestamp made sense only within a view, a timestamp was concatenated with the view ID of the view in which the timestamp was generated. This pair, view ID timestamp, was dubbed the Viewstamp. And so Viewstamps are born. My thesis notes tell me that I gave these special timestamps their name. And that's how the replication technique got its name, Viewstamped Replication. Viewstamps made it possible to determine inexpensively how much each replica knew in a view. The state of the replica with the highest viewstamp for the previous view was used to initialize the state in the new view. This replica was selected as the new primary if a view was formed successfully. The correctness of Viewstamped replication algorithm depended on this interaction between transaction processing and the view change algorithm. Transaction processing guaranteed that transactions were serialized properly. It guaranteed further that a transaction could commit only if all its events were known to at least a majority of replicas. The view change algorithm guaranteed that events known to a majority of replicas survived into subsequent views. Therefore, events of committed transaction would survive view changes. You can read more about the machinery of transaction processing and how it interacted with the view change algorithm in the paper and in my doctoral dissertation.
Thank you, Dr. Oki. I understand that you first presented the paper at the conference of the 7th Symposium on Principles of Distributed Computing. What was the response to your paper at the time?
Joran, I presented the paper in Toronto, Ontario, Canada in August of 1988. At the conference, the response to the paper was muted and fairly neutral, as I recall. The chief criticism seemed to be that I was advocating multiple backups in addition to the primary when it was already expensive to checkpoint information and messages from a primary process to a backup process, as in Tandem and Origin. Back then, researchers cared about the number of messages exchanged, the number of rounds of messages, and the size of messages, because networks were slow and latency was high. Here I was saying that you'd incur 1.5 rounds of messages during the view change algorithm, and that the primary had to send messages to multiple backups to propagate events. Yes, this was considered expensive. The view change algorithm was also criticized as being not that interesting. I was mystified. Viewstamped replication was the first algorithm based on primary copy and multiple backups that actually worked in the presence of both node failures and network partition failures. Little did I know that 24 years later, the ideas in Viewstamped replication would gain increasing traction and renown.
With all of this going on, what was the year 1988 like for you?
Larice, my final semester at MIT was the busiest, most incredibly intense, and intellectually satisfying and exhausting at the same time. Not only was Barbara Liskov and I writing the PODSI paper, but I was also writing the dissertation furiously to meet a deadline for commencement. I was also preparing a thesis, seminar talk for job interviews. I also spent one weekend in Cherry Hill, New Jersey to compete in an amateur ballroom dance competition. After sailing through the thesis defense, I spent a sleepless week incorporating the changes from my thesis committee of 3 professors into the dissertation itself. And finally, Barbara Liskov signed the title page, and I submitted the thesis to the EECS department. I attended commencement at MIT, surrounded by my family and friends. It was a joyous occasion for me and a celebration of my intellectual achievement. I spent the summer as a postdoc at MIT. Then I embarked on a 7-week trek through Europe. I joined the computer science laboratory of Xerox's Palo Alto Research Center in the fall of 1988.
After 1988, what happened next? Did the industry catch on quickly, or are you still amazed to hear from people discovering Viewstamped replication and realizing its value in the data center? What are some of your favorite anecdotes over the years?
Larice, sadly, no. As far as I could tell, the paper languished in obscurity, certainly in industry. The ideas were incorporated into other MIT research projects like the HARP file system and Byzantine fault tolerance, and that was very satisfying to me. Did it catch on quickly in industry? No, it didn't, as far as I know. A friend of mine left Sun Microsystems in the late 1990s and joined another well-known company. Over lunch, he told me, "Your paper is famous." He was a fellow PhD, so I knew he was talking about my research papers. I said, "Which paper? I have several papers." He said, "Your paper on Viewstamped replication." "Really?" I said, "Why?" He said, "Well, for our particular service, we were really intrigued by the properties of Viewstamped replication and have implemented it." At a startup I joined about a decade after that, several engineers recognized my name and asked whether I was the same Brian Oki who published the paper on Viewstamped replication. Again, I was both astonished and gratified that there was interest even then in a paper I published back in 1988. The paper has stood the test of time. These engineers said to me that the paper appealed to them as engineers because it contained snippets of a concrete implementation that they could easily understand and an informal proof of correctness that was more intuitive.
Can you tell us more about the SIGOPS Hall of Fame Award? How did it feel to receive the SIGOPS Hall of Fame Award yourself in 2012, along with Barbara Liskov, 24 years after your paper was published?
Joran, I was astonished to hear that our paper had been selected for induction into the ACM SIGOPS Hall of Fame in 2012. I was at a startup company when I received email from Barbara Liskov. We hadn't been in touch for a few years. She said simply, "Our paper on VR is receiving an award." I thought, what? Really? Why? I was still in disbelief. After 24 years of relative obscurity, or so I thought, the paper was finally being recognized as a practical approach for designing highly available distributed services in an asynchronous network to maintain consistency of data in the face of concurrency and failures. The chairman of the committee that selected 4 papers in 2012 said this in email that Barbara forwarded to me. On behalf of the SIGOPS Hall of Fame Award Committee, it is my great pleasure to let you know that your paper, Viewstamped Replication, a new primary copy method to support highly available distributed systems, by Brian M. Oki and Barbara H. Liskoff, in proceedings of the 7th Annual ASEAN Symposium on the Principles of Distributed Computing, POTSI 1988, is one of 4 papers selected for the award this year. Congratulations. He went on to say, the SIGOPS Hall of Fame Award was instituted in 2005 to recognize the most influential operating system papers published at least 10 years in the past. Once again, congratulations on your award, and we hope to see you at OSDI in Hollywood. I agreed to attend in person to receive the award at OSDI 2012, the prestigious Operating System Design and Implementation Conference. Since I lived in California, it was easy for me to attend, but Barbara couldn't make it. I cannot tell you how excited I was. I hadn't attended any systems conference since SOSP in 1999. This was the ASEAN Symposium on Operating System Principles, because in 2001, the dot-com bust in Silicon Valley meant companies didn't have money to send people to conferences. The chairman of the committee that selected the papers for the Hall of Fame award told me that he would like a photo of me to display during the award ceremony along with Barbara Liskoff's. He said that nobody knew what I looked like, since I hadn't attended any research conferences for more than a decade. That was really funny. I was told that the awards would be announced during lunchtime. I arrived at the venue in Hollywood, California, and sat down at a table. It turned out that a professor was sitting at the same table. He saw my name tag and asked me, smiling, "Are you the Brian Oki of Viewstamped Replication fame?" How do you respond to a question like that without sounding arrogant? I said simply, "I am Brian Oki." He said that Viewstamped Replication was a more natural systems approach to solving the problem of strong consistency with replication. That was gratifying indeed. The chairman of the committee that selected the papers said this aloud when he introduced the paper. The paper introduces a replication protocol very similar to what is now known as Paxos. That protocol has become the standard for consistent, fault-tolerant state machine replication and is widely used in data centers to keep the state consistent despite failures and reconfiguration. I sat back astonished. It had been 24 years since the original paper was published in 1988. That the protocol was widely used in data centers was a revelation to me. After the award ceremony, numerous people came up to me to congratulate me on this very high honor from the research community on operating systems. I also took the opportunity to hang out with 4 of Barbara's students who'd graduated with their PhDs in the 1990s.
What an incredible moment, and true test of time for such a special algorithm and paper. And it's so great. Thank you so much for sharing these incredible anecdotes with us, Dr. Oki. Looking back now, what are some of your special memories in working with Barbara Liskoff during the course of your dissertation?
Joran, I learned several valuable lessons from Barbara Liskoff, which has shaped my thinking about systems. First, I learned an important principle, which I've applied in much of my working career. If you cannot state your system invariants, then you don't know what your system is doing. Second, I learned how to be a better writer of technical papers. This lesson has been extremely important in my working career because the ability to explain simply and clearly is a valuable skill. Third, I learned the importance of systems thinking. That is, systems thinking is looking at a whole system in its entirety, not just the parts. It is understanding how those parts relate, interact, behave with each other to implement the overall behavior of a system. Fourth, I learned how to think more precisely in an informal way without worrying about the formalism. Stating guarantees precisely and succinctly is a skill that can be learned. The skill has proved to be extremely valuable in my career because it has unearthed correctness problems that would have otherwise manifested themselves in just really weird system behavior. My doctoral dissertation has an informal proof of correctness where the conditions are stated precisely and intuitively.
Thank you very much, Dr. Oki. So you mentioned how important ballroom dancing was for you while working on your dissertation. Do you still dance to this day?
Larice, I discovered ballroom dancing at MIT. It was exactly the social outlet I needed to balance the intense intellectual demands of the PhD program. It started out as a fun thing to try during the January independent activities period. Before long, I found myself enjoying it so much that I attended weekly workshops in the smooth and Latin American ballroom dancers, went to practice sessions and social dances at MIT. Ballroom dancing was social, athletic, performance, and musical all wrapped into one. In the last term at MIT, while furiously writing the dissertation and the paper and preparing for job interviews, I competed over one weekend in the Eastern U.S. Ballroom Championships at Cherry Hill, New Jersey, in the Bronze International Foxtrot and Tango. When I moved to California to work at Xerox PARC, I continued dancing and competing, and now I dance socially for fun. Joran and Larice, I continue to be astonished at the interest in Viewstamped Replication 33 years later, but also gratified that the paper stood the test of time. Thank you for your persistence in finally tracking me down and arranging this interview with me. I appreciate it very much.
We also are very happy to have you here. It's been a pleasure.
It truly has. Thank you, Dr. Oki.
Let's have a 5-minute break before we continue. Hello, everyone. We're back. Took a while. Sorry for the wait. Let's go with this nice interview to James, who is the DJ from from the stories. James, let's just jump right into it immediately. So, what was your first memory of Viewstamped Replication, and what makes it special to you as a protocol? Like, what sets it apart from other stuff?
Yeah. Hi, Loris and Joran. Nice to be here. And thank you, Joran, for that nice intro and making me seem cooler than I actually am in the introduction. So I learned about this stuff at MIT when I went there to be a grad student. And two things were going on at the same time. I was taking a class in distributed algorithms with Nancy Lynch, who's a bit of a pioneer, big figure in the distributed algorithm space, so proving algorithms correct. She's well known from something called the FLP result, which is the Fisher-Lynch-Patterson proof that consensus is actually impossible unless you have some bounds on timeouts and latencies. So I was learning a lot about distributed algorithms. And at the same time, I was working on Byzantine fault tolerance in Barbara Liskov's group. So Barbara was Brian Oki's advisor. And so Byzantine fault tolerance, for those who may not know what it is, it's basically it's a replication protocol that works when the participants can not only fail, but they can also be malicious. So algorithms in Byzantine fault tolerance, typically you say you need to have 3 F+1 replicas to be able to handle F failures. So if you want to have one malicious party in your group, you need to have 4 replicas total. And what's interesting about ideas like a Viewstamped replication is that they're just very, very fundamental. And my personal feeling is there's very few deeply fundamental ideas in computer science, and everything else kind of gets based on top of those. And the idea of a durable replicated log is probably the most fundamental idea in distributed systems, and is a building block for a large fraction of the distributed systems out there. And so I was working on Byzantine fault tolerance. At the same time, I had an appreciation for VR, was also working, studying algorithms like Paxos at the time. Obviously, things like Raft hadn't come out yet. There's other formulations of the problem, like virtual synchrony out of Cornell. And coming to the realization that there's a lot of ideas that were very fundamental, but maybe weren't that well understood by the community, and maybe weren't kind of really didn't have really a broad understanding that these things are all kind of the same idea. For me, what makes VR special, I mean, it was very pioneering. It's extremely useful. I think if I was to compare VR to, say, Paxos, which is obviously a very important protocol in itself, Paxos is an agreement protocol, and VR is a state machine replication protocol. Right? So very, very similar in essence, but Paxos is used to agree on one idea, and VR is just used to chain these together to build a replicated durable log. Right? Both basically the same thing to a large extent, right? But to me, VR makes a lot of sense because it solves a lot of the problems that you run into that you can take consensus and build state machine replication on top of it, but it is pretty non-trivial. And I think VR bakes these together, which made it special to me.
Makes sense. Thank you very much. So, how did the idea to collaborate with Barbara Liskov in the Viewstamped Replication Revisited paper in 2012 come about? Like, what was the development process? How long did it take also?
Yeah, I was thinking about this, and I was just musing on the fact. So Barbara Liskov is a very famous computer scientist, and this was around at the time she got the Turing Award. And there's a principle named after her called the Liskov substitution principle. It's an important principle in object-oriented programming, I guess, in polymorphism. And she didn't even know. I had this great interaction with her where she had never heard the phrase Liskov substitution principle before. And I asked her about it, and she was like, what is a Liskov substitution principle? She knew the idea, but she just didn't know that people were going around calling it the Liskov substitution principle. And similarly, it's very easy to be in academia and a little bit insulated from what people are thinking about your work outside in the broader community. But we got to the point where I think two things were happening. One thing we realized is that there just wasn't a reference for VR that was written with the perspective we had gained by that point in time. We'd worked on Byzantine fault tolerance, and I think in hindsight, a lot of the ideas seemed a lot crisper to us after decades of reflection. So we felt like the community we owed the community a good explanation of this work, particularly during this point in her career where she was getting a lot of visibility with her Turing Award, etc. But also this observation that a lot of papers were coming out called like Paxos made simple, Paxos made live, Paxos made, I don't know what the other one's called, more simple or something. And there's a lot of these practical, and it became clear that that there was no shortage of people trying to explain very similar ideas. And that it's not at all easy to explain this stuff. So Joran did a great job in the intro. Not all easy to explain this stuff in a way that is impossible to misunderstand. And that also is very easy to hand wave away implementation details that are not at all simple, right? So in particular, I think Google did some work around how to change the Paxos made live, I think. And so questions like, how do you change the membership of the system? So you start off with these additional members. How do you change that membership over time? We hadn't written a reference on that ourselves. And so the desire was to write a reference material for how to build the system in a way that's kind of adequate to be implemented in practice and get this down properly. I don't think we kind of had ambitions beyond this. We didn't publish it at a major conference or anything because it's retrospective work to a large extent, or there are some new additions to it. So it was a tech report, and frankly, I was very pleasantly surprised when Joran reached out and I found out that there was people reading this work and that people were enthusiastic about it, because it had kind of fallen off my radar as well. We wrote this and didn't realize people were appreciating it.
Thank you.
Well, thanks, James. I really love the paper, and in particular, what I love about it is, like I said, that remix that you did of the view change. So it's an elegant round-robin view change algorithm. It's deterministic, and that seems to be at the heart of Viewstamped Replication Revisited. How did you arrive at that? Did you start out with a more random leader election protocol, maybe where replicas vote for themselves, a more selfish protocol, but then maybe the protocol must deal with the problem of split votes. You have to redo the election, and then you try and get away from that. Now you've got to also introduce latency penalty of randomized timeouts. Or did you always have the intuitive deterministic leader election protocol in mind that sidesteps all of this?
This may be a short answer to the question because it was always deterministic in our minds. And the reason for that, I think, reflects the thinking within the group and the thinking of how kind of Barbara's students think or are taught to think. And thinking in terms of very clear abstractions, very provable properties. And there's a lot of great randomized algorithms out there with very high performance, very high performance, or with great emergent properties. But we had a real kind of deterministic thinking towards problems where we want things that are a very crisp mental model. And we didn't really want races in the algorithm, even if they were virtuous races, if that makes sense. So where in, say, Paxos, for example, there's, you just keep trying until someone wins the election. What felt intuitively, sound to us was a deterministic proposal. But the other thing also is we'd been working in Byzantine fault tolerance. And in Byzantine fault tolerance, you're working in the presence of faulty actors. And we had various protocols where you would do, there'd be scenarios where you're trying to figure out who is, you're working on lots of different protocols at the time. Scenarios where you're trying to figure out who is a good participant, who's a bad participant. And you kind of go around round robin, and we have guarantees where in each step, at most you kick out one good party and one bad party. So at the end, once you've kicked out 2F of them, you have F+1 good folks left. So this thinking around determinism and round robin behavior, I think, really led to that. And yes, so it's great for Byzantine scenarios where you can't trust the participants, but I think it also leads to it's a more intuitive crisper definition of the problem in the non-Byzantine sense.
Yeah, I never realized until now that was that Byzantine model that influenced it. But it makes so much sense that you would want to just move around equally so that no one can rig it. Oh, thanks.
So how did your Viewstamped Replication revisited paper compare to the rest of your research at MIT? And how did you feel when the paper was done? Like, were you surprised about the uptake to Viewstamped Replication revisited?
Yeah, that's an interesting one. So I'm not sure if folks, some listeners may have been in a PhD program. There may be PhD programs in different countries and different universities. What it's like to be in a PhD program in a group like Barbara Liskov's is you don't just go there to do your thesis, right? You do a whole bunch of random work for a long time, and then eventually you just happen to write a thesis, right? So we were doing a lot of different work in various areas. And my thesis happened to be on distributed transaction coordination, so somewhat independent. So how did VR compare? Well, VR, we almost didn't consider research at the time. We considered that almost as something we wanted to kind of take ideas we'd already had and kind of write them up for the community. And so I mentioned we hadn't really published it that widely. I think upon reflection, one mistake I certainly made back then, and something I do better now that I'm in industry is this idea that ideas don't really have tremendous value unless they're impacting how other people think, right? If you have the world's greatest idea and no one hears about it, it doesn't matter, right? And so we wrote this paper and we put it up as a tech report, and that was basically it. I don't think at the time I'm not sure if Twitter was very big back then. It probably wasn't, and people weren't really blogging about their ideas that widely. But I was the same me. I did a terrible job of promoting this back then. And years later, Raft came out, for example, which again is kind of the same protocol, right? But they did a way better job of communicating it, And I remember for a little while being bitter that Raft was getting all the play and that it was kind of the same protocol as the stuff that had come beforehand. But then, in hindsight, realized that, what Raft achieved was getting people excited about these ideas because they got out there and it got people to buy into this stuff. So, like I said, I was very surprised when Joran reached out. I was really excited to hear that people were paying attention to this protocol. I personally think this is the most intuitive. I mean, of course, I would say this because I was involved in the work, but I think this is the most intuitive formulation of a fundamental idea, and kind of also the original formulation of the idea. So I'm glad that there's a bit of a resurgence here. Just that, and I could have done a lot better job at the time of kind of instigating that back then. How does it compare to the other research I was doing? I was reflecting on this. I was working mostly in Byzantine fault tolerance, which at the time was not maybe not that widely respected. I think I got a lot of people to tell me like, "Why are you doing this work? This is useless. No one's ever going to use this stuff." And I heard Brian's presentation earlier talking about when he presented his work, he wasn't getting a lot of people weren't falling over themselves to say, "Oh, this is amazing," right? Yeah. But Barbara has always done work like 20 years ahead of its time, and only people notice it 20 years later and they say, "Oh, this is amazing," right? I'm less good at that stuff. So I worked in Byzantine fault tolerance. I was fairly early in that field. Ended up getting out of it because I just kind of got convinced maybe that it wasn't that practical. And now, I've got good friends running cryptocurrencies that are based on Byzantine fault tolerance. Like Byzantine fault tolerance is a big idea in the cryptocurrency world. So, that's something I got to give Barbara credit for is, these great researchers having an ability to not only come up with ideas that are significantly ahead of their time, but also have the commitment to stick by them and not be discouraged that, you may not get adoption for a decade if an idea is ahead of its time.
Thank you. I have a follow-up question to this. So my next question after Joran is going to be about after your the academia phase of your life. So I think you touched upon very interesting points, and I have a curiosity as as an external observer. I've never really participated to academia past getting my bachelor, and a little bit more after that, but not much. So I agree a lot on your point about basic ideas, like core ideas, over on which other ideas basically crystallize around. And also, you've seen how effective in the end was. It took a while, yes, but in the end, writing a paper on the pure core idea of Viewstamped Replication, which I think you did a great job, by the way, as and as a non-qualified reader, I could understand it. That was amazing. And so what makes me think is, like, why aren't all papers like this? And I'm guessing, obviously, on one side, it's hard, right? It's not immediately easy to understand what's the right angle to approach an idea, what's the core thing, what to take away. And so I understand that side. But my wonder is there also some kind of, like, maybe attitude problem in the academia that makes it harder to produce this kind of stuff?
Yeah, this is a great question. So I'll try to give a short answer. I could talk for a whole day on this topic.
Yeah.
Right? Because the best academic research is incredible, right? And medium-tier academic research is sometimes useless, right? And that's the interesting thing about the difference between academia and industry. In industry, you're actually solving a real problem right in front of you, and it gets tested and it's deployed and it works or it doesn't, right? Academia, it's different. So what's different? Well, you have a lot more freedom. Yes, you have to apply for grants, etc. But at a place like MIT, you have a lot of intellectual freedom to really do what you want to do. But you don't have problems in front of you necessarily, because you're not necessarily building stuff, right? You're thinking of ideas, right? And you're actually building prototypes and testing and stuff. So when I left academia, I was just flooded with ideas, because all of a sudden I was building real systems and had real problems and had customers to serve, right? So most of my biggest ideas have happened after leaving academia. As for why, so personally, I think there's some papers in academia that's amazing. So I was looking at a paper a little while ago. I think it's just called leases. It's when they invented the topic of a lease, and it's just the paper on leases. And they're like, wow, that's a whole new idea. That's a paper. That's awesome, right? So this kind of old school academic research I love. There's a bit of a trend sometimes in academia now to just write, I was a systems researcher, but write systems papers where you just talk about a system, right? We built this thing, but without really calling out necessarily why I should care about the system. What makes it unique? Because there's in all research, there's the thing you did, and then there's the core idea that has durability. Right? So I've done, for example, I wrote a Byzantine fault tolerant protocol called HQ replication. I don't think anyone's using that in the wild, and probably they shouldn't. Probably they should use like the basic, Miguel Castro's Byzantine fault tolerance idea. But there were kernels of ideas in there that went on to inspire other work, etc. So the great thing about academia is you have a work, and there's the work in itself, and there's what it inspires. Yeah? And oftentimes the thing that inspires is far more important. So why the paper's not just talking about the thing that it inspires? Well, it's hard, right? It can be very hard. Like, it's easy to look back in hindsight and see what the important part of a project was. But at the time, not so much. Even if you look at like a great industry research paper, like the Spanner paper, right? So everyone knows Google's Spanner work, right? Incredibly influential. What was the point of the Spanner paper? There was a lot of existing ideas, right? A lot of that stuff was not novel. The true timestamp stuff was very novel and very interesting, right? The fact that you could build a database on as a distributed system with state machine replication and stuff was not at all a new idea from an academic perspective, right? So why was Spanner interesting? Well, one, there was some revolutionary ideas around, say, hey, now we have atomic clocks and GPS clocks, and now we can do interesting things regarding time that you couldn't do before, and that we can have bounds and we can store transactions. That's interesting. And the second thing that's interesting is Google says, hey, we took these theoretical ideas in academia and we actually did them for reals, and now we run Gmail on them or something, right? And then that's very valuable too. Okay, I guess it works, right? And so the challenge with academia sometimes is you can't write that level of paper, right? When I was in academia, I could never write a paper and said, oh, and now there's 1 billion customers. I went to Dropbox, and the biggest project I did there was probably building the storage system there, which, at one point had approximately 1 million disk drives, right? It had 400 million customers. It had 3 exabytes or more, something on multiple exabytes of data in it, right? That stuff's that's real, you know. But you know, so that it's very tough in the academic environment to come up with both inspirational ideas and then prove them out with a real world, like demonstrated, test that they work, especially in systems. And you're seeing now a lot of the big systems work has come out of Google and Microsoft Research and these places where they have the resources to do these tests. Right? I still think there's a huge role for academia, but it can be hard. It's very hard to think of an idea sitting in your desk and come up with an idea. Yeah.
Understood. Thank you.
Going back to what you said about surprises, James, that you were surprised when I reached out to contact you about the technical report. And also speaking of Dropbox, so I just wanted to share, before I ask you for some behind the scenes anecdotes, I wanted to just share one of mine. So I had seen what you had done at Dropbox, the whole storage infrastructure team there, that, you know, with Magic Pocket, how you built this massive storage system. You just moved all of Dropbox's data out of the cloud, put it in the truck, into the loading bay, you know, into your own storage system. So I read up everything. I watched all the talks, and some of the talks you did on like durability theater, like are we trying to just use the formulas for fault tolerance, or are we actually engineering systems that we know are going to be pretty safe? There's a big difference. But I watched that all made a huge impact. I think even in what we do in TigerBeetle, there's a lot of that trying to come through, where we're verifying the production stuff as it's running in production. We're self-testing, checking. But the huge surprise for me was that I actually heard about Viewstamped Replication from Heidi Howard was saying, you know, this is the pioneer, take a look. Martin Thompson, Mark Brooker, and so I checked it out. So I went and looked at Viewstamped Replication, and I knew of all your work. And then I see, on the paper, James Cowling, and I thought, okay, this is the one that TigerBeetle will use, because it's obviously brilliant.
Thank you for that vote of confidence. I appreciate that.
Yeah. So thank you for that, and I'm so glad we could get in touch. So it basically it seems like many of Barbara Liskov's past students, obviously Brian Oki, Sanjay Gemawat, also a huge hero of mine, along with Jeff Dean. But Sanjay, Miguel Castro, Dan Ports, yourself, you've all gone on, it seems, to do something with Viewstamped Replication, and also to have an impact on computer science industry in your own right. What are some of your special memories in working with Barbara Liskov? Can you share some behind the scenes anecdotes, and what were the best lessons?
Yeah. I was thinking about this. You know, I became a much better engineer after I left grad school, for sure. You know, I don't know if I was a good engineer in grad school. You know, because I learned when I became an engineer, we'll talk about later on, but I learned how to build pragmatic, maintainable things. You know, I think the thing I learned mostly in grad school, and from Barbara in particular, was kind of how to think. If that makes sense, you know. And if people think about going to work with someone like that to learn some facts, it's a waste of time, right? If you want to learn some facts, go learn them yourself or whatever. You go there to learn how to think, right? And that comes from like arguing with a really smart person about something, right? And, you know, walking around, and many times, you know, I'd be there on a weekend in the office, and we'd find some bug in a protocol. And I remember just pacing back and forth on my phone talking to Barbara, and she was at home, and we'd be, you know, trying to conceptualize, you know, distributed system interactions in our heads, and you know, having those arguments with a smart person who, one, like, is very, very adamant about crisp mental models and what is the abstraction. I mean, Barbara's kind of the pioneer of abstraction in computer science, if you could say that. And so what is the abstraction that represents this? So being in that environment, getting really pushed, I think, is helped me kind of learn to think, I suppose. Also helped me learn to kind of maybe present ideas to folks. You know, and I'll throw some of that research under the bus insofar as there was some pretty inscrutable work that went on where, you know, important papers that, like, an important protocol is buried under a file system and a distributed database and this and that, right? This is where, like, the inspirational thing was kind of hidden. And so learning that, you know, it was really, the onus was on me to make sure the person I'm speaking to can really understand my ideas and can not misunderstand them. I learned a ton. I mean, like day-to-day life was, it was grad school. My office was covered in bicycle parts. Everyone, I was fixing bicycles. We were building a tandem bicycle. It was, it was a bit of a mess. We spent all my life in there. Argued a lot about ideas. Worked on papers together. And anyone who's been to that environment knows what it's like. You work on a paper, for some reason you don't finish it. You do an all-nighter the night before, and it gets finished. The paper's 16 pages, and it has to be 14 pages by the deadline, and you have 10 minutes to somehow get the paper from 16 pages to 14 pages. So you go and cheat, and you change all the settings in LaTeX. So it squeezes the characters closer together. And then I remember Dan Port's going there, and I think it was Dan Port's, was really good at having no orphans at the end. I think it's in typography, it's called orphan, when you have a paragraph and the last line has only a few words in it, right? So we'd somehow change the wording so every paragraph kind of filled the full line, And so that, these like useless skills that we had to develop in the process. So that was what life was like. But yeah, look, I think in hindsight, you mentioned a bunch of names, and it's very flattering to be put into the same category as some of those folks like Brian and Sanjay, etc. But I think if I was to claim that I've had some influence at a place like Dropbox or at my current company, I think it's really pushing very hard on simplicity and very hard on making sure we actually understand what we're doing. And that makes me slow. I'm a bit of a slow engineer, because I have to really understand what I'm doing. But that's an idea that came from working with Barbara, where you just can't hand wave your way through a distributed systems protocol like that. You just can't duct tape some things together and hope it's going to work. You have to really understand it from first principles.
Shall I go? So let me see. I have a question about after your time at MIT. So you joined Dropbox, if I understand correctly. So do you have some fun stories that you can share about your Dropbox days?
I have a lot of yeah.
Yeah, and what did you learn about storage?
I should have asked this question, Luis.
Yeah, I have a lot of fun stories. And again, this is one thing I took up for years. I mean, I was there 8 years, and I had a great time at Dropbox. That was my second education. MIT may have taught me how to think, and Dropbox taught me how to be an engineer. Baptism by fire, because I very quickly ended up being the lead for the storage team. And the project at hand was to move Dropbox's storage off of Amazon S3 to our own infrastructure. And I think when we started, we probably had about 150 petabytes, and then, or maybe 7. I think we had 70 petabytes when we started working on this stuff. And then by the time we were done, we had hundreds. We had exabyte size data, and so that project, in hindsight, was a resounding success. I mean, it was done in 2 years basically, and start to finish, and huge financial outlay, but it worked out, financially advantageous in the end, and there was no data loss, etc. But yeah, I was doing 16-hour days for a while then, just because I wanted to, because it was super fun, and the people I was working with were just, and I have a company now, and my 2 co-founders were the 2 guys I was working with the most, and we would work long hours. It was interesting. We joke about being like kind of the odd couple, because Jamie, I was this MIT PhD guy, and they're like, who's this out of touch MIT PhD guy? And then Jamie had dropped out of an English literature program at UCLA, so he was a college dropout, English lit, startup guy. Seen a lot, done a lot of real stuff. And Sujay was an intern. I think he was 20 at the time, an intern who'd come to do an internship and never come back to school. He was a math student. And we all came from very, very different backgrounds, but I love those guys. I love working with them. And so we would work hard, and we'd have a little band. We'd have jam sessions at night, and we'd play music. And everything that could have gone wrong went wrong. But I mean, as Joran was saying, I have talks about this stuff, like the durability theater talk, where you have to, when you're doing real world stuff like this, you have to build very, very, very simple systems, because simple systems are composable, and they they continue to work when they even start to break, right? And they're understandable. And you have to foresee the worst case scenarios. And we had situations where we were at one point, in academia, I was thinking about just IDs in the abstract. At Dropbox, I was thinking about building out data centers and writing the software for it. And at one point, we were bringing up, I think, 40 racks of servers a day, and these are fully loaded racks. I think they had 8 4U chassis with 100 disks in them each. So these were heavy, these like car weight racks. At one point, they were so heavy that the casters compressed and we couldn't roll them. And then we're like, how do we get them in time? At one point, the loading dock was just full and we couldn't get them. I'd laid out this nice little plan for we put them this row, this row, this row, so we'd have power diversity and all this kind of stuff. That doesn't work when you're trying to wheel them in, And at one point we had 2 trucks crash in the same week. 2 tractor trailers crashed that were carrying our servers. Ooh. They had no data on them. We moved all the data over the wire. So a lot of we had a lot of fun working, just coming up against the edges of these of real world problems. Issues where, for example, you get a 600 gigabit network link and you're getting less than 40% of traffic through it because it turns out it's made of bonded 40 gigabit pairs and the load balancing is not working great between them because you're using FIFO load balancing, and there's all these emergent properties that come out at scale with where the connections you reuse are the ones on the slow links, and the connections that you're not reusing are the ones on the fast links. All these interesting emergent properties come out. So that battle testing stuff is fun. Wow. But I think it's very important you don't let that get to you and go back to duct tape mode, right? You got to take all this stimulus. If these things are going wrong, these things have to get done. How can we try to come up with a clean, abstractions to solve these problems?
Yeah. So you were you were having trouble. You had to work with containers, but literal containers.
Real containers, yeah. Yeah, real containers.
And then you had docking issues as well with the caster wheels.
So many things. Yeah. When we started using Rust, when we were using, that was a big gamble. We were using Rust before it was GA because we needed something. We were using Go for most of our infrastructure, but we were scheduling the disks ourselves. We were doing our own disk head scheduling at a certain point. We were using the draft specs from the manufacturers for how the SMR disks work, shingled magnetic recording disks, because they weren't out yet, and we were using Rust before it was GA. And all these things were hedged. If they didn't work out, there was backup plans. But yeah, we had to be riding right on the edge there.
Yeah. Now I always noticed how you guys were really early adopters of Rust. So I think that's just a good message for the Zig community as well.
Yeah, it's never too early.
Never too early. Yeah. So James, you touched on that there's as you build these big systems or you build any system, things will always go wrong. You've got these emergent properties. As engineers, how can we increase the probability that things are correct and working? How can we debug issues in our thinking?
Yeah. There's a few. The number one thing I've already said, I'll say it again: build simple shit. Excuse me for saying that, but build simple stuff. It's just and simple is not easy, right? Simple stuff is not and building things that look simple is really, really hard and takes thinking. So the simpler something you build is, the more, any complexity compounds in cost over time, right? Number one, keep it simple. Number two, the talk floating out there, I'm sure somewhere, it's called the power of zero, which I've given about, if you can get to a system if you can build systems that are verifiable. So this was a little bit related to your question about the deterministic view change versus randomized view changes. I like verifiable systems. And so when we design Magic Pocket, for example, the mapping from an object to the disk it's on, or the disks that it's on, it just goes through a few layers of databases, right? And so what would happen is people would come from academia particularly, and they'd say, well, why don't you use a distributed hash table? And and that could automatically rebalance, etc. Right? And my argument against that, one, they can be fairly complicated, and databases are, not easy to run, but easy to conceptualize. The second is if you have a database which has mapping from A to B, you can write a verifier job that walks over that database and makes sure everything's in the right place, right? So designing systems for verifiability is really important. So if you have emergent properties in your system that you can't prove at runtime, then you have gaps that maybe you have problems that you don't realize. So we have this talk about the power of zero. I mean, if you get your system to 0 errors, if you truly know that in production right now, I have 0 errors, that if something shows up, you can move really fast and fix it. It's very empowering. It takes time to get there, but if you can get things to 100% correct, it actually accelerates development so much, because then you can build stuff, you have good testing frameworks, you get that to production. You would probably be stunned at what goes on at all the big tech companies, that the big $1 trillion tech companies, and how many inconsistencies they have on their servers and how many weird bugs there are floating around, right? And it takes a lot of work to get systems to that point.
So are you saying, James, with the power of zero, it's about decreasing your noise ratio to like zero, so that when you see a blip, okay, we go fix that. It surfaces the bugs quicker.
That's a great way of framing it. So, and one other thing I'll say, so I had these models for disk failure rates, and do we have enough copies of our data? Are we replicating it appropriately, right? And so you can write formulas around Reed-Solomon coding, etc., and figure out, given failure assumptions, how many disks you need. And you might say, cool, how long will it take to one of the inputs is, if we lose a disk, how long will it take to replicate that somewhere else? And you might say, well, we can do that in 48 hours, right? We have automated systems that can do that in 1 hour typically, so 48 is very safe, right? But if you have a disk corruption and you don't notice it for 3 months, right? Because no one's read that data and you can't trust the smart checks on your disk, right? Then you've completely blown out your failure assumptions, right? So it's not only reducing the noise ratio, but also understanding the current state of your system. And there's so many systems out there where you just don't know, right? The classic example that almost every company runs into one point is they have a database and they say, cool, we should have backups. And they create database backups and they never test the backups. They never restore their entire company from backup. And I can guarantee you, when you try to do that, it's just not going to work. Right? Every company does this. It's all these stories. My co-founder, Jamie Turner, has a great podcast. Actually, I'll plug. It's called The Downtime Project. And they go through postmortems of failures that have happened at big companies. And all the big outages that have happened, and they talk through what happened and whether it was handled appropriately, etc., and comment on it. The Downtime Project. And a lot of these errors is like protections that were never tested, and so they never work. Right? Yeah.
Wow.
I'm sure people listening to this thinking, "Oh, I've never tried restoring from backup either." Right? It's probably not going to work. It's probably not going to work.
I was just thinking something for TigerBeetle that I need to just make a to-do note, because we know about this, but other people need to know, so I need to
if you
to do with scrubbing.
Yeah, if your system designed to handle failure, you need to inject those failures. Or how do you know that it actually works?
Good point. I need to take a look at my Zig News backups. I actually have 2 setup backups at all. I'm at the Galaxy Brain stage where you don't even have those. But by the way, so thank you, James, because I with this last couple of questions, I just realized one thing that I think is gonna be a great point to make in the future for Zig, which is that since you were doing your due diligence with the design and the architecture, you had, if you will, like engineering risk budget to spend on a bet like Rust. So what I'm thinking is that if I want to write something to tell companies to try out Zig and give it a chance, even though it's risky, right? Because we are pre 1.0, etc., etc. I guess one good metric also for me to understand how much should I be interested in a particular company or whatever, it's to see if they're doing their due diligence, because if your company is like, if your infrastructure is always on fire, like if your company is writing C# and it's a Microsoft shop and everything is always broken, even Python becomes a risky bet. This might or might not be related to my previous job experiences. I'm not gonna say either way,
Yeah.
but yeah, if people want to try out Zig, like the people that do their due diligence with everything else, then they can try a bet and they can have big winnings if they get it right. Like I guess it happened to you with Rust.
The way I like to think about this is because I've been in various roles at the company, and I've been like a senior engineer, but also like a fairly senior manager. And there's always this trap engineers fall into where they think like management's the enemy and like, oh, my VP doesn't understand and all this kind of stuff, right? And oftentimes the VP understands completely well, but they have a different set of priorities to you. Maybe they don't want the stock price of their company to go to zero, right? And so I always try to, when I'm making engineering decisions, is think about how like the execs are what are the motivations for the decisions executives are making, and I should incorporate those same motivations, right? So if I go to management and say, hey, I'm gonna go write the storage layer in Rust, and if it fails, the company's over, don't worry, just trust us, right?
Yeah.
Then they should say no, or they're not doing their job right, you know? But if you're an engineer who can really get things done, I think the engineers who can truly get things done, especially in a larger company, are the ones who have the empathy for how leadership's thinking, right? So it's like, cool, we've de-risked the product by this, right? We have a working prototype in C#. Now we want to, we think we can get these benefits from trying this new language, right? These are proposals that kind of have empathy for the business at the same time as wanting to improve the engineering.
Makes sense.
I remember Jamie saying at the time that Rust was great because memory is expensive and you were trying to literally save every single byte and bit that you could.
Yeah.
Yeah.
I'm not sure I can tell you how much money we saved off switching to Rust, but also the rewrite. We saved significant double-digit percentage. I think it was probably 30+% we saved. And the reason for that is, we would sit there and stare at a pie chart of where our money's going on servers, and it was broken down like sheet metal, the chassis rails, the CPU, the network, all this kind of stuff. And the RAM was getting bigger and bigger and bigger. And we wanted that pie chart to be like disks and everything else on the top. Right? And so we needed to get really memory efficient. And there was a lot of other things that came from the rewrite. Also, the Rust switch was also a rewrite of the storage layer, which was abstracted away and componentized, so we could do that, right? If it didn't have good software engineering discipline, we absolutely couldn't rewrite the whole system in Rust. It's too much work, right? But we had segmented this out. We could then have a new fleet of machines on this new version, and the benefit of the rewrite made it much cleaner, much more efficient, and we really, really reduced how much memory we needed and how much CPU we needed.
Awesome. So what were the most important things that you learned while working in the industry that you didn't know while working, like while you were still in research at university? And with that you know now, so from your industry experience, how would you have written Viewstamped Replication Revisited today?
Oh, yeah. Well, the first thing I ought to say, because just to give some credit to my co-workers and co-founders, like they're so talented. And like, I think I came out of grad school for some reason, this probably happens quite a bit. You think all the smartest people go to MIT or something, and that's not true, right? that's the people who wanted to go down that path, right? So I came out, I was like, whoa, there's some incredible people who went through different parts of life, right? So that's the one thing. And also, we should always, just have empathy. I always like to, in any conversation, go into the conversation thinking the other person's a smart person. So if they don't agree with me, let's figure out why they don't agree with me. And so that's served me well. I mentioned this earlier, but ideas only really matter if they have an audience, right? And I don't think I was very good at pitching ideas back in academia. If I did it again, it would look completely different, because VR would have come with a reference implementation, which it didn't, which, I'm thankful Joran's working on right now. We would have published a reference implementation that would have existed, a decade ago now, or more. People would be using it. And I would have blogged about it, and that probably would have become the de facto thing. So I dropped the ball back then. Just this wasn't how I was thinking. Would have written a paper, would have written a talk, would have written blog posts, would have written some real code, put it on GitHub so people can use. Right? I think it would be quite different now. Now there's differences also. Protocol might look different because I have a bit more perspective now, right? For example, one thing we tried hard in the VR paper was to avoid disk syncs at all costs. I don't care about that most of the time for my work now because, every now and then we want to power cycle the whole fleet anyway. And so taking checkpoints and writing them to disk is a good idea in general. Typically your replicated log is going to get long enough that you have to flush it to disk eventually. And so the nature of the protocol would have been slightly different. But yeah. Biggest difference would have been how it was pitched. Yeah,
makes sense.
I'm glad you mentioned that because this was something I didn't get to in the intro talk. But something that sets Viewstamped replication apart from the other state machine replication protocols that I've seen. I've seen a few, but I haven't seen all of them. But the one thing that really sets it apart is it seems to be the only protocol that is correct if you're only working with memory. A lot of the others, if you want to get your view change correct, you have to write to disk first. But the 2012 version, the remix, the view change, everything is correct if it's all in memory. If your machine crashes, you've also got an extra battery included. So you've got all the batteries included, plus this extra battery, which is the recovery protocol.
Yeah,
it just seems
suitable.
Yeah.
Sorry. It's suitable for scenarios where, for example, you want to run a replicated log on SSD, or in memory for like a write-ahead log, and then you have stuff getting pushed to databases in the back end. I don't know of other protocols that have done. At least at the time, I think it was the only, to my knowledge, only protocol that operated completely in memory. There may be work since then. Yeah.
Because it just seems like a much better place to start, because once you've got your consensus protocol correct only for memory, then you could go to disk. But it's like a nice to have, and you could use it when you need it. It just I've been thinking about this the last few weeks, and so thanks for doing that, because
excellent.
It just, with TigerBeetle's storage fault model, it makes things much easier.
Perfect. That's great. I'm glad it's being useful.
Yeah. James, I just wanted to ask you, what does the future hold for you? Can you tell us something about this new stealth startup you've co-founded, along with people like Jamie? Yeah, you've got a startup, Jamie Turner, CJ Jayakar. Like, what a fantastic team.
Yeah. We're just rebranding right now. So the new name is called Convex. The website's convex.dev, convex.dev. You'll notice there's nothing on that website other than an email that you could use to email us if you'd like. It's basically some of the core team that built a lot of the story stuff at Dropbox. Jamie and Sujay went to rewrite the sync protocol later on, and we ran a lot of the story infrastructure in general at Dropbox. We have a little team, and we just hired a guy, Braden Walker, who was the tech lead for databases at Dropbox, one of my favorite engineers, and Indy Kare, who came out of Google, ran a lot of the engineering for the Google Photos team. So we have a great little team and two awesome part-time folks working with us. And we're building a new backend for serverless web applications. So the idea is, the kind of characters who would be right now using Vercel or Netlify because they want to build a web app, but they don't want to run their own, server side, their own infrastructure. These platforms are great for static content and kind of semi-dynamic content. There's not awesome support for truly dynamic content when it comes to reactivity and automatic caching, etc. So we're building a platform for that. We would love to, it's very early days. It's not that stealthy insofar as I'm happy to talk pretty openly about it. But at the very core, we have what we think are quite an interesting idea where you write your queries in TypeScript. We kind of execute them server side for you. We track the reads and write sets of these transactions, so we actually know what your data is doing We can send in validations to you to automatically refresh your data, etc. So we're building a backend platform, and I'll jump the gun right now and say we're also hiring. So if people are interested, come work with us. Right now, it's that we're a Rust and TypeScript shop. But hey, we're open-minded, and yeah. So right now, we're funded, but we're very small, and so we're looking for a couple of awesome distributed systems folks, some good, really good full stack / front end people. Anyone who's a really enthusiastic kind of front end developer who also cares about dealing with NPM and build pipelines and all sorts of stuff. That's also someone we're interested in. So yeah, please reach out to me. Just info@convex.dev. Yeah.
Awesome. Convex.dev. Any other particular skill that you're looking for?
Oh yeah, thank you for mentioning that, because if you play drums, that's an extra bonus. We had a little band. Jamie, Suja, and I we played a little. We had a little cover band. It was called the Hot Pockets because we were building this magic pocket at the time. So the Hot Pockets. So Jamie's bass player and Suja and I guitarist. I sing. But yeah, if you're a drummer, that's a big plus. So mention that in your
Awesome.
mention that in your message as well.
Okay, so let's do a very quick round of questions from the audience. There's already a couple that I want to, I guess, rebroadcast to you, James. And there's also going to give a couple of minutes to the viewers to write a couple new if they want to. So first, let's start with a couple of maybe not super serious questions. And actually, the first one is for Joran. So does Joran do audiobooks? Do you do audiobooks?
You're gonna have to now, yeah.
Joran, I think people love your voice.
Oh, do I read? Do I like produce them?
Yeah, exactly.
Yeah, I do actually.
Really?
I read a whole lot of Julia Donaldson children's books for my daughter, and then the two of us, we record them. And she says, you hear it on tape, she says, Papa, record. And then we go and in the car, we listen to our stories. So I've got a whole collection. Yes. Just get in touch with me and I'll get you those Julia Donaldson.
Or time with Joran.
Illustrated by Axel Scheffler. Thanks.
Okay, second question. What was the bandwidth of the tracks that crashed?
Oh, that's a good question. We could kind of guess how many those racks held. So we had, I think at the time they were probably 10 terabyte disks. We probably had 100. We had about a petabyte per chassis. We probably had 8 petabytes per rack at the time, which is a lot. It's a lot of density. And so I have no idea. I don't remember how many were in the truck, but let's say there was at least 20. So you can do the numbers. So it was it was probably in the 100 petabytes. I don't know how fast the trucks were driving.
Oh man!
Now we replicate the data more widely than that. Interestingly, we moved all the live data over the wire. We had a rule that, in fact, the Dropbox takes data privacy very, very seriously, and so we wouldn't have disks leaving the data center. They get shredded on site when they're done, and so and for consistency reasons, etc. We were live migrating data and verifying, etc. So we actually moved all that data over peering links. But yeah, the trucks were coming off. There was a lot of bandwidth coming in truck wise though.
That track must have been a very expensive packet collision. So okay, more serious question. There's a serious question from Andrew. So from Andrew Kelly, our BDFL. So I'm quoting, "I'm getting married next year. Do you want to DJ my wedding?"
Send me an email. It's amazing. It is funny. So Dan Ports is a researcher in this area, and so specifically, I was DJing his wedding, He married I probably shouldn't tell everyone's personal details on the air. He married another researcher in distributed systems as well. So they're all they're very much in the field. And in fact, Sujay actually spent time working with his wife. So everyone knows everybody. It's a very small community. So that's a strong maybe. Send me an email.
Awesome. Well, thank you very much. Joran, is there anything else that you want to ask our guest?
Oh, just to say a huge thank you, James. It's been such an honor and privilege and learning so much really all the way from you. Thank you.
All right, appreciate it. Write simple systems, everybody. And it's been nice chatting.
Thank you. That's
Thank you.
great advice. So
Thanks. Bye-bye.
bye-bye. Now let's move into a short intermission while the full Tiger team comes on stream because we have our final segment of the show. So be right back. Don't go away. It's not going to take long. Okay, we are here for the final segment and meet the Tiger team. I think only Isaac is missing, right? Because he's somewhere else.
Yeah.
Yeah. Let's introduce everybody. Joran, you can go first if you want.
Yeah, Isaac's just away actually on, he's been hiking in the Swiss Alps, taking a nice break, and he sends regards. He's going to catch the stream afterwards. Just to introduce myself, my name is Joran. I'm an engineer at Coil. I'm the lead for TigerBeetle. And my favorite movies are War Games, Sneakers, and Zig SHOWTIME.
Awesome. Thank you.
Hey everyone, so I'm Adrian Bailey. I was at Coil until very recently. Just started a new business of my own, heavily inspired by James. Yeah, I'm happy to say TigerBeetle is an idea that we had a very long time ago, and that would still just be an idea if it wasn't for Joran. So very excited to still be part of this journey and seeing the amazing stuff the TigerTeam are putting together.
Hey guys, I'm Don. I was also at Coil and I was working with Joran on TigerBeetle, and it's been really amazing watching this thing progress. Just well done again to the whole team. It's fantastic. I've since left, and I'm now also working with AD at the new company. So yeah, so again, just to say, like, this is really awesome. Yeah, thanks.
Hi everybody, I'm Jason Brewer from Haarlem, all the way in the Netherlands. I recently joined the Coil and I'm part of the TigerBeetle team. I come from a largely payments background. I'm very excited to be getting my hands dirty in Zig, and so far so good. Very impressed with what Zig has to offer thus far.
Hi everyone, I'm Sarah. After initially studying a BA in philosophy and psychology, I switched over to doing a BSc in computer science, which I finished at the end of last year. So I joined Coil at the beginning of this year as a junior software developer, and I'm very excited to have recently joined the Tiger team now as well.
Awesome. Thanks, Sarah. And I'm TD. I've recently joined the Coil team as well. It's been about 2 months now. And it's been awesome to see what the team has built. It's been awesome to see the things that it was built on and the reasons and all of the thinking. Yeah, so it's great to be here. Thanks.
Awesome. Thank you, everybody. By the way, Sarah, I also love philosophy, and I'm actually happy that I ended up studying computer science because, like, don't lose your hope. I think that computer science can be a nice door into philosophy. So if you go at it in the right way. So
yeah, there's definitely a lot of room for crossover there.
yeah, so I'm awesome. Okay, so we've learned about Viewstamped Replication. We had interviews with the authors of the original papers. At this point, we've been talking about this game where how can I say, there's somebody trying to break everything, right? And I guess my question at this point is, we're talking about, like, also there's this $20,000 number floating around. Like, is it a game or is it real?
It's real, Lars. It's real. There is a real $20,000 up for grabs for anyone who wants to participate in this program, and everything you've read about it, everything you've seen so far is real.
Awesome.
And the rest of the team are going to share a few details on the specifics. So I'll hand over to Don.
Cool. Yeah, guys. So this is a bug bounty challenge. So there are 3 different tiers of bugs. The first of which is a correctness bug. This is a serious one that violates strict serializability or leads to data loss. So if you find one of these, then you could earn a bounty of up to $3,000. And I'll hand over to Sarah to explain the next tier.
Yeah, so if you find a liveness bug, that's a bug that actually crashes TigerBeetle, then you could earn a bounty of up to $500. And you can read some of the details explaining the definitions and the T's and C's associated with these on the actual Viewstamped Replication Made Famous repository.
Awesome. Thanks, Sarah. But it's also, in addition to being a bounty challenge, there's a little bit more in there. So we think Zig is just really amazing. And so for every bounty awarded, there'll be an additional 10% of the value of the award that Coil will match and send over to our friends at the Zig Software Foundation for the amazing work that you spoke about a little bit earlier on doing, Larice. And over to you, Joran.
Thanks, Ellie. And there's something else that also just got real. Bishop's Vopper is real. And you get to have the Vopper as your R2D2, like your sidekick to get you into the state space. So you can run the Vopper yourself. It's in the repo, and that's got all the instructions how to run it. And the Vopper is going to inject corruption on all the replicas in the cluster. It'll corrupt like a minority of an operation, never more than a minority. And it'll inject all different kinds of latencies in the network. It can simulate the whole network, simulate packet loss, or a whole lot of faults. There's some things it doesn't do that are there for you to figure out. We didn't want to make R2D2 too amazing, but R2D2 is pretty cool. So the Vopper, you can run it, but it's also more than just fuzzing, and it's more than fault injection. It's also totally deterministic. So if you run the Vopper, and if it crashes TigerBeetle or does something that looks suspicious, you can actually get the seed and just replay the whole thing. And you can replay it again and again and again, because obviously you can't just submit the Vopper seed. You need to, if you find something, you actually need to dig in and now apply your skill and understanding, and then write your Bishop report. But the other thing that the Vopper is also going to do is it's not just fault injection, fuzzing, it's not just deterministic, but it's also a state checker. So it's going to check every single state transition in the functionator, aka the state machine. And it'll also check if that's valid based on the client requests that are in flight. So have as much fun running the Vopper as we have had. And over to you, Jason.
Yeah, so lastly, for a VSR Made Famous channel on the TigerBeetle Discord server, where you can come and hang out and ask any questions regarding the bounty.
Nice. I'll make sure to add a link to the Discord, or like an invite to the Discord server, also in the description of the video afterwards. So what's next, Joran?
What shall we do? Shall we see how much time have we got left?
Yeah.
Okay. Is my screen share live, Larice?
It is now.
Okay, give me a second. So what we're going to do now is we are going to make all of this live. So you can head over to Coil HQ on GitHub, and then the repo of Viewstamped Replication Made Famous. And then you can go and click watch the repo. And what we're going to do in a few seconds is we're going to push it live. So let's do our countdown. Shall we launch this consensus challenge?
Let's go.
Okay. Everybody ready?
$20,000. Make it real.
Here we go. Let's make it real. 10, 9,
8,
8,
7,
6,
6,
5,
5,
4, 3, 2, 1.
2, One. Wait for it. Wait. Let the games begin.
The games begin.
Yeah.
Oh, Joran, I'm still
Awesome.
seeing a dark screen though on your screen share. Am I missing something?
Oh, that's okay.
okay.
We've got it.
We are live.
It's
We're
live.
live,
It's
yeah.
on the repository.
Yeah. Yeah. And I
Uh,
see Yigal was the latest person to watch, so that's awesome, Yigal.
Oh, there we go. I can bring it up on the stream. Let me show it to everybody.
Awesome.
There we go. Oh, yeah. Nice. Viewstamped Replication made famous. Well, awesome. Thank you very much. So, as they said, if you have any question, you can reach out to them on Discord. You have a way of debugging and simulating and injecting failures in the protocol using the Whopper. I don't know, at this point, please put in the effort, get a bounty for yourself, help us unlock the 10% bonus for the Software Foundation. That would be a very nice way of donating not your money to the Software Foundation. And yeah, that's it. So is there anything else that you guys want to say before we close the episode? At which point I'll ask Joran to remain for one final minute. So maybe we can go in
Before
order.
the rest of us go, Loris, I wanna just say big thanks
Yeah.
to you for all of the help and for everything you've done. It's been a lot of fun being part of Zig Showtime on this episode and the previous one. So and Don and I are going to continue being contributors as well to TigerBeetle. You know, we're at Fanboys, our new business. We're using TigerBeetle in the products that we're building. So we're very excited to stay close to the project.
Awesome. Thank you very much.
That's it for me, and thanks again for everything.
Who wants to go next? Don, you want to go next? Shall we continue that way?
Okay, sure. Yeah, I mean, pretty much echo what Eddie said. Yeah, and it's and I think that's something echoed what James said. Is like surrounding yourself with like really intelligent people and like bouncing all the ideas off. Like it really played a part in TigerBeetle, and yeah, I was happy to learn from someone like Joran as well. So thanks for all of that, and to the rest of the team for organizing this. It's really cool. Yeah,
Thank you. Who wants to go next? Jason, maybe?
Not much from my side, just looking forward to what's in store.
Awesome. By the way, just so you know, we have a ton of people in the community from the Netherlands. I don't know precisely why, but like there's at least 5 that I can count of, like very active people. So just so you know, like also another reason why I'm mentioning it is because we're gonna try to have meetups soon. So you might have the opportunity of meeting other Ziguanas in person if you happen to like meetups.
That's awesome. Yes, gonna have to yes, keep an eye on that.
Yeah. Thank you, Sarah.
Yeah, not much else to say. It's just really such a wonderful experience to be part of such a positive team and such a welcoming community. And yeah, you guys should all watch the repository, and I suspect we'll have our first issue up in no time at all.
Awesome. Sally?
Just let the games begin. We can't wait to start to see those tickets and issues and interesting findings come through. And definitely let us know how you're progressing, what you're listening to, what you're getting inspired by. Yeah, let the games begin.
Okay, thank you very much. So let's have the final outro. I hope everybody doesn't mind. I'm gonna pull everybody out of the live room because I want to have a short one-on-one with Joran. So thank you again, everybody. What's up, Joran?
I just want to say thanks to the Tiger team. You've done an amazing amount of work, huge effort from everybody. To Isaac also, it's been amazing and it's pretty magical. This is the experience of one of the technicians. It's been pretty magical. And thanks to Brian and James. I never imagined that we would get the opportunity to talk with you and learn from you both. Thank you so much. And Larice, to yourself, all the production work, and to Andrew, who let me have the rights to his Cabbage Man track that we used as our intro, and for Zig, for giving us Zig. Thank you that we can work with such an amazing language. To the whole Zig community for supporting, and especially finally, just to dedicate this whole event to Professor Liskov. Through your work over the years, you've made a huge impact on all of us. Thank you.
Awesome. Well, okay. Thank you again, everybody. Joran, let's have our one-on-one. Don't worry, there's not going to be anybody watching us. I don't know, maybe just a few people. So I wanted to, first of all, say thank you very much. I've done some production work. You've done probably way more than me. Your talk in the beginning was amazing. Also, Joran is the person who actually chased Dr. Oki, James Cowling. So thank you also very much for organizing this stuff, because I am very confident that I would not have been able to pull that off on my own 100%. On top of that, so the countdown was supposed to show the final numbers, right? At the end. But I don't know, Joran. It seemed didn't the timer start like at 25 or something? I don't think we exactly followed the original schedule. And in all honesty, my conclusion after running Showtime for a while is that honestly, the only winning move is not to have a fixed schedule.
I think so too. It's a strange game, Consensus, Larice. Sometimes the best move is to do another Zig Showtime.
Well, thank you very much. And with that, I think we can finally end the episode. Bye, everyone.
This is how we